So 2.2, we said that the boundary conditions of the tangential component of E, we did the 2.0 was for D, and we were able to say that if we are moving from on an interface from medium 1 to medium 2, and we took a pillbox. Sometimes some of the books you find the pillbox being of this shape, with the other dotted part showing you to be in the other medium on a given interface. But we took a pillbox by taking a part of this, and if this is the tangent to the interface, we took this to be N1, 2. That is the normal component from medium 1 to medium 2, or the unit normal direction vector, when this was our ds, and if the pillbox was of height h, which is so minimal, very tiny, because you're moving from the medium 1 to medium 2, you're just taking a little bit of the interface down into medium 1 and up into medium 2. And then we came up with M12. This is our D2. And this is our D1. We got that the dot product of D2 minus D1, and the normal direction vector is the same as the free surface charge density on the interface. On the circumstances that you don't have any surface charge density, or you don't have any free charges on the interface, which is so common, then you end up having that D2 is equal to D1. So we say that D is continuous across the interface. So it's crucial that we first understand the behavior of D and E. Now the boundary conditions on the tangential component, of E. So we shall draw our stochastic loop, but before then I'll have to draw an interface. Which interface I'm drawing is what I've been having here. Did you deliver the message to Zachariah? Yeah? So this is the normal, and then I'm taking, I should have had 2 of these, like this, to make sure that the way this part of the stochastic loop goes here, so just make your eyes compress this white stuff into like a sheet of paper, so that this thing here at the bottom and the chalk piece, so take this to be so small, okay? So we are having this part of the stochastic loop going into the other medium, and then this part of the stochastic loop also going into this other medium. And then we shall be able to go through the algebraic gymnastics to find out how E behaves across the interface. And take this part here as the normal from medium 1 to medium 2. So I will use these dotted lines to show so this will be my N1, 2, that is from medium 1 to medium 2. As you can see when you look at it on the board, really, medium 1 and medium 2 that do not come out easily, but when you look at them in the sense of this interface, you know that medium 1 is down here, and medium 2 is up here. And this is our stochastic loop. And I can put these dotted lines. And I'll be having E2 along here. And I'll be having E1 along here. That is the electric field density in medium 1 for E1, and E2 is the electric field density in medium 2. So let's take the current loop, or this loop be moving in an anti-clockwise direction, and take the loop to be of height h and of width dl. So this is dl. We shall also take the, excuse me, which class are you going to attend? You have the vector along the interface, or tangential to the interface, being t cap. So I can. T is tangential because, as I showed you here, the stochastic loop along the other part of the stochastic loop is also tangential to the interface. You get the idea? I could have drawn this T along here, but then it doesn't make sense. We have to draw it along this part of the interface, of the stochastic loop, which is also parallel to that. And when we say tangential, it means it is parallel to a given surface. And then we shall draw B, which is perpendicular to this is our N12, this is our T. We shall draw B, which is perpendicular to the plane that contains N12 and T cap. But I can't draw anything towards me like this. The only thing I can do is try to make it look like around here. So I will call this one B cap or leaf. B roof or B cap is perpendicular to the plane that is containing T and N12. That plane is this one here. If I put this thing here like this, that is a plane, which is a vertical plane, which is having the normal, which is that wire going up, and which is also along this other part which comes my side of the stochastic loop. T is along this part here, and N is this one. This is the plane. B is perpendicular, which is towards you, perpendicular to this plane. But I cannot draw it coming towards you artistic along the board, otherwise it will be a dot. So that's why I'm trying to draw it just like you normally draw the words, and then you start doing like this, and like this, putting right angles there to show that they are perpendicular, but if you look at them, they are not perpendicular by our eyes. Get a point? Okay, so if we can define a couple of terms, N12 or cap means that, this is the unit vector. unit vector normal to the interface. Normal to the interface between media 1 and 2. Between media 1 and 2. T cap or T roof is the unit vector tangential to the interface. Tangential to the interface. And of course, the other part is, or the other label on the diagram is B cap, which is the unit vector of B. The unit vector of B. And B is a vector, so you put 1/2 R on top, unit vector B, normal to the plane connecting N12, or the normal from medium 1 to medium 2, and T roof, which is the unit vector tangential, and is called the binomial, And this binomial is given by the cross product between T and N12. So we have that where T roof is equal to B cross N12. I don't know. In the notes, you'll find that at times I say T roof is equal to N12 cross B. The cross. So I don't know which one do you feel comfortable with? This inverted V or the X? Inverted V. Pardon? Inverted V. It's more convenient in which way? X is more convenient in which way? So by definition of the curl of the vector, then we have that B that the curl of E is equal to the limit as ds tends to 0 in 1 over ds close the integral along a line either dl, and this is where dl is equal to T roof dot delta L. And this would be the same as limit as h tends to 0. I should have said C, no, I think so. HDL, that is the area is the ds is the same as the length times the height, the length times width. And then we have that this goes to be E2 minus E1 dot T roof And then we put our, is it square brackets? Then they are, and then close our brackets, implying that our limit as h tends to 0, e nu h, b cap or roof, dot the curl of e is equal to e2 minus e1 dot t. You now have the diagram in your minds, so I can take the liberty dabbing off. So we move on to the, this implies the limit as h tends to 0, that is, as you get so closer to the interface as possible, then we have that HB proof that the curl of E is equal to, close it, is equal to E minus E1 that T or unit tangential vector. But we said that T is the same as the cross product of the binomial vector, unit vector, and the normal across the interface. And 1, 2, implying that our limit as h tends to 0 h be roof that the curl of E is equal to B cross N12, which is our T, and then dotted with E2 minus E1. We very well know that the dot product is it associative or distributive? That is, A dot B is equal to B dot. That is called what? So then we have that this is equal to E dot N12 cross with E2 minus E1. And then we have by interchanging, this is by interchanging the dot product and the cross product. By interchanging the dot. Now I'm just trying to do your mathematics, especially the mathematicians beginning physics. So we let the limit as h tends to 0, h the cross product of, the curl of E would be equal to N12, then we cross it with E2 minus E1 plus some constant lambda times the N12, and let's call this one our equation 1 for purposes of convenience. Thus, if we deduct N12 N12 roof with equation 1, we shall generate or yields limit as h tends to 0, N12 roof that h, the car of E, equaling to, if we that N12 and N12, we multiply by their magnitudes. The magnitude is 1, 1. Then the cosine of the angle between them, they are parallel to each other, to itself. N12 is parallel to itself. The angle is 0, so you will end up with 1 times lambda. So take the direction of the normal to be along the z. We took the direction of the normal to be along the z direction. For example, if we have our directions being x, y, then z, of course this will be along the z, along the y, although you are used to this being I, this being j, and this being the k. So if we let or take the normal, take this normal here, this wire here, to be along the z component, meaning along the z direction, to equal to z, then we shall have that the limit as h tends to 0 into h Kali along the y Kali x minus Kali x Kali y will equal to, I have to first do all this, will equal to lambda. I mean, this car of E is normally given by, or can be given as, if we take the component of E along the x, along the y, and along the z, and take the components of E along the x, component of, before then we have to first take care of the partial differentiation for the delta function. So we are having the Kali by Kali x for the x component, Kali by Kali y for the y component, Kali by Kali z by the z for the z component, and then we take care of the electric field intensity along the x, electric field intensity along the y, electric field intensity along the z. If you cut out this curve, normally what we do is that if we want the x component, we cover up this and then take the determinant of this. If we want the y component, we shall have the y component part, take the determinant of that, and if we want this, but of course when you are taking that of y, you must make sure that you take care of the negative. So it's a plus, minus, plus. So what happened was, if we took the normal to be around the z, then we would be looking for the z component and we would cover out this, and that means we would have Kali by covered out that. So we have the Kali by Kali x ey minus Kali by Kali y e x. This is the expression here that I covered out this and then took this minus, this minus that. This is like this minus that. And this is where I got this Kali by Kali, Kali y by Kali x minus Kali by Kali y dx. Yeah. That was now replaced, or was used to replace the car of E here. So since the derivatives Kali Ey by Kali x, Kali x, Kali y are finite, that is, you can get their value, you can work them out. Since they are finite, then we can say that our limit as h tends to 0, h multiplied by the Kali Ey by Kali x minus Kali Ex by Kali y is equal to 0. So that gives us the left-hand side being equal to 0. If the left-hand side is equal to 0, and the right-hand side is lambda, it means our lambda is equal to 0. So this implies that the whole of our left-hand side is coming out equal to 0, implying that our lambda, which is our right-hand side, is equal to 0. Thus, we can say that N12 roof cross E2 minus E1. Taking interest, I am struggling all along. I keep making sure that I have the vectors. If you are answering my questions and you forget to put this half-headed arrow, I cancel it. That's how mean I can do it. All in the name of science. This would be equal to the limit as h tends to 0 in h, the curve of E. But you know very well that even from the word go, we say the mere fact that we have these outward electric field lines, our curve, when we try to curl out these field lines, we get 0. Sure? But even if we didn't do that, if we just said that let E equals minus grad V, and we take the curve of E, this would be the same as the curve of minus grad. And what happens when we get the curve of a vector, when we get a vector and cross by itself, we get 0. So even by this method, we can still be able to show that the curve of electric field density is equal to 0. You try to curl the electric fields, you don't get anything. They disappear. So if our curve of E is equal to 0, then we would finally say that N12 roof cross E2 minus E1 is equal to 0. And we can comfortably say that the tangential component, the electric field density is continuous across the interface. So it means that what goes in at the bottom, medium 1, shouldn't disappear anywhere. It should only cause polarization, but whatever you feed in here as E1 should be able to come out along here, as long as you are talking of when you are within the interface. So when you take the component of this electric field along the interface, what came in and what should be going out on the other side, there is continuity of that electric field across this interface. You won't have anything disappearing within your dielectric materials. Question? Any question? Okay. Let's consider a case where we take, let's consider an interface. Let's consider an interface between two perfect. You know, they are very so you have perfect interface. I will not draw the artistic interface, and this artistic interface can always. So this is our interface, and this is medium 1 at the bottom, and this is medium 2. So we are having our interface here, and then we are having our medium down and our medium up. And then we are having our D and A entering here. So D1, E1. If you remember the electromagnetism, we did something of the sort. D2, E2. So if this is having epsilon 1 as the permittivity and epsilon 2 as the permittivity in medium 2, and if these are approaching the interface at an angle theta 1 to the normal and coming out at an angle theta 2 to the normal, the continuity of the normal component of D will give us so continuity of the normal component normal component of D. So we had that our N12, that D2 minus D1 is equal to 0 for continuity when our sigma F is equal to 0. Since there are no free charges, at the interface. The reason for this is that these are perfect linear dielectrics. You won't find any free charge on an interface of two perfect linear dielectrics. How can? Because when you get these two dielectrics and insert them in the plates, they will have the charges, bound charges drifting. So if this was a positive part and this is the negative part, you would have the bound charges, positives drifting to the other side of the negative, and the positives and negatives drifting the positive terminal, and you won't find any free charge at the interface. The only free charge you find we have our free charge density at the plates, and this is a free negative, and this is free positive. So in a linear, or at an interface of two linear dielectrics, you wouldn't find anything called free charge at. So that means our N12 that D2 minus D1, which was equal to sigma free, this would equal to 0. What were you talking about?
I was wondering about that
This D.
Is it D1?
Semicolon. But what were you talking about? Because you realized. And when you told him, you became more happier than him who was asking. Then we have that this would imply that the normal component in the 2 is equal to the normal component in 1. And that normal component, we can get the normal component which is along here, which would be the cos, such that we say that this is D2, the normal of D2 here is this component, which would be D2 cos theta 2, equaling to D1 cos theta 1. I can take this one as equation 1 or star, whatever you want. So continuity of the tangential component of E we had that N12, which we can simply take as N, okay? Because we know that we are talking of the normal component of the interface from 1 to 2 cross E2 minus E1 is equal to 0, implying that, of course, where N cap is the normal to the interface, from medium 1 to medium 2. So this would imply that the tangential component in medium 2 is equal to the tangential component in medium 1, or this continuity across the interface, implying that the tangential component, I've dubbed it off, but the tangential component would be along the interface, which would be stretching the theta, so stretch sine, compress cos. So we have that this would be E2 sine theta 2 is equal to E1 sine theta 1. If we take this as equation 2, then we can comfortably say that from the D and E being related or proportional to each other, D is proportional to E, whereby the proportionality is because of how emissive the medium would be. And that is D equaling to epsilon E. This would imply that D1 is equal to epsilon 1 E1, D2 is equal to epsilon 2 E2, and equation 2 divided by equation 1 would yields or implies that E2 over E2 cut theta 2 cut Is it equation 2 or equation 1? This should be equation 1 divided by equation 2. That's when we get our, be sure, d2 of, equation 1. If it is equation 1, that's when we have d2 over e2, and we have a cos over sine, which is a cot theta 2 is equal to e1 over e1 cot theta 1. Or if we substitute in for d1 and d2, we can say that epsilon 2 cot theta 2 is equal to epsilon 1 cot theta 1. And this would cover our part of boundary conditions. We now have two boundary conditions well suited. That is for when we are talking of perfect dielectrics, then we have the M1, 2, that D2 minus D1 is equal to 0, and N1, 2 plus E2 minus E1 is equal to. So if you have two perfect conductors, dielectrics, the normal component of the displacement vector is continuous, so is the tangential component of the electric field density. So we meet Thursday.